Before we can start solving any differential equations and being able to apply them to any real life applications, the first thing we should probably do is get some terminology under our belt so that way we understand the phrases and the intent of where we're going through with this. So let's define a differential equation. So a differential equation is any equation that relates an unknown function and one or more of its derivatives. And we're going to see a bunch of these throughout the course, and you've probably seen them in some of your other courses. There's actually two different types of classifications of differentials. There's these things called ordinary differential equations. And an ordinary differential equation doesn't contain any partial derivatives. For most of you, if you've ever solved a differential equation in any of your physics classes, engineering classes, or even your Calc 1 or Calc 2 classes, it was most likely an ordinary. A higher level type of differential is going to be called a partial differential equation. So we have these ordinary, and then we have a partial differential equation. Partial obviously contains a partial derivative, so the derivative of a term with respect to a specific variable. And then we talk about the classification of these differentials. So one of the ways that we classify a differential is by talking about its order. And the order of a differential equation is the same as its highest derivative. So if there's a third derivative, the order would be a third order differential equation. We talk about these linear differentials. Linear essentially says there's a function of x or a function of t times y, or the dependent variable. All right, so in this problem, or in this example that we have, the x is the independent variable, and so let's kind of make that known throughout, that x is our independent variable and y is the dependent variable. It'd be nice if we could solve it for y. That doesn't mean we always can. And in other words, get an explicit solution, but there's a lot of times that we can only get an implicit solution. In other words, a solution like xy plus xy to the third is going to be equal to a sine of x or something like that. In other words, we can't solve it for y. All right. There's these things called families of differential equations, and there's two types of solutions. So we have families of differentials, and then we also have these general solutions. All right, so when we talk about a general solution is a family of solutions that satisfies a differential equation. Most of the time, the family is defined with the plus c. Okay, so it's like y equals some function of x plus c. That would be your general solution. However, we have a particular solution, and the particular solution is a specific member of the family. So for instance, we might have f of x or y equals f of x plus 1 to be a specific member of the family. And to determine whether we want plus 1, minus pi, whatever it might be, what we have to do is we have to use the initial value. So the initial value that belongs to a differential equation tells us which member of the particular family that we're looking at. Now we're going to see this geometrically, and we're also going to see it analytically, in other words, algebraically, in a few moments. But first, we should be able to classify differentials. In other words, if you look at a differential equation, you should be able to tell me what the order is. You should be able to tell me whether it's linear or nonlinear, and then you should be able to tell me what the order is of this. Okay, so let's go ahead and see what we can do to be able to classify these. So the first one that we have this 5x dy dx plus y sine x equals e to the x. So the first question is it going to be ordinary or partial? And we look at the derivatives. And we've seen this notation before, or hopefully we've seen it before. If we've seen it before in either Calc 1 or Calc 2 and it doesn't have the partial symbol, then it's ordinary. All right, so first of all, we'd say that this is indeed an ordinary differential equation. Is it linear or nonlinear? So let's go back to the definition of linear. And linear basically says that we have a function of x times y, first derivative, or second derivative, or third derivative, and then a different function, possibly, times another derivative of y, all the way down to a function of x times y is equal to some function g of x. And that's precisely what we have. We have a function times first derivative, we have a function of x times y, and then we have it equal to f of x. All right, so this is most certainly a linear differential equation. And then the last thing we do is we look to see what the order is of this differential. Clearly the order is 1 because we're only dealing with a first derivative. A next example. So we have this differential. So third derivative of y with respect to x minus second derivative of y with respect to x plus 7x, first derivative of y with respect to x plus 2 e to the y equals 5. So is it ordinary or partial? And once again, these differentials are all types that we've seen in Calculus 1, Calculus 2, physics. So it is indeed ordinary. Is it linear or nonlinear? Now, it looks linear, doesn't it? Except for the fact that we have e to the y. Right? If that was just 2y, then we would say that it's linear. But unfortunately, because we have an e to the y, or we have like a sine y, or even like a something like that, it just has to be y. It can't be anything else, like even a square root of y. This is going to be nonlinear. And then finally, notice that we have an order of 3 as the highest derivative. All right, so the order of this differential would be 3. Okay. A third example, fifth derivative of y minus y equals third derivative of y plus second derivative of y plus x squared ln x. All right. We might choose to rewrite this. So fifth derivative of y minus third derivative of y minus y double prime minus y is equal to x squared ln x. Right? So in other words, just write it into the potential form of a linear differential equation. Right? So is it ordinary or is it not? Is it partial? And again, this is ordinary because it contains a type of derivative that we've seen before in Calc 1, Calc 2, physics, etc. Is it linear? So I look down the line. I have y to the fifth, fifth derivative, third derivative, second derivative. I just have a y. None of those are affected by any other operative, such as a square root or a natural log on the y's. So it is linear. And then finally, is it going to be, or what is the order of this? And obviously the highest order is the fifth order. Okay, so we have a fifth derivative, which is the highest one. So we have a fifth order differential. Finally, we have this structure, which maybe you've seen before, maybe not. And this is a partial. All right, so for those of you that have never seen a partial derivative before, whenever you have this symbol, this is the partial of y with respect to t. So partial of y with respect to t. And so from there, we can right away just say that it is partial. And since this course is ordinary differential equations, I wouldn't expect you to do the rest of it. Right? So when you get to that point, just leave it alone and you're good. Okay? All right, so now that we've had a basic overview as to how to classify differential equations, the next thing that we're going to look at in the next video is we're going to look at how to solve some really rudimentary differentials, what their families would look like, and then finally how to trace the initial value for that.